So AI has been getting a lot of attention lately, and it's highly probable that you use it on a regular basis to cheat on your assignments. However, this is a physics project, and you may reasonably ask how these two seemingly unrelated topics are connected. This is the question we set out to research, and throughout this video, we will give you a quick rundown of our findings and how we applied them.
Let's start with an example. Imagine if we have an oscillating mass spring system, something that looks roughly like this. Imagine the spring is then stretched, and you take a snapshot of the spring at a random time after it is released, and it starts to oscillate. Recall what we learned in class about simple harmonic motion, and pause the video to tell us whether you would be able to predict the trajectory of the mass when given the position, velocity, mass, and spring constant at any snapshot across a 10-second time interval.
Well, that was kind of a trick question, because there's really no way to solve for the trajectory using just algebra. In order to actually solve for the position x of t, you would need to use calculus. If you are interested in the solution, you can check out section 2 of our paper. This is where the idea of the deep model comes into play.
So let's get into what a deep learning model actually is. Let's say you have an image of an animal and you want the deep learning model to recognize the animal in this image. First, we gotta represent the deep learning model. Here is the image of the deep learning model. Notice how there are these balls, called neurons, connecting each other via these lines. When we run this model, the input image gets transformed into a matrix, which if we were locked in for math, you would know is a list of numbers. Think of these neurons as the types of questions you can ask. When the model is run, each neuron modifies the list by storing what information they gained from their question, allowing the model to make a prediction based on the last layer's matrix because it effectively includes all the information from the neurons before. The output matrix then gets transformed into the model's prediction. For example, if the input image shown was an image of a cat, the model's output matrix, assuming it's accurate, would be converted to the word cat.
After the model outputs its prediction, it is compared to the actual output to check the model's accuracy. The model then goes back and self-adjusts its connections or parameters to increase its accuracy. This process, called backpropagation, is repeated for multiple inputs to optimize the model's predictions via a loss function that measures the error of the model compared to the actual truth. If the model is smart, over time it will be able to produce correct predictions and learn the behavior of the system in question.
Now let's connect these ideas back to the oscillating mass spring system. In our experiment, we trained the model on a variety of data where we changed the initial position, velocity, and mass attached to the spring. Note that the g here represents the mapping function between our three variables and the trajectory. Essentially, it shows how the model is learning to map relationships between these variables and the predicted position of each of these data points. We now go to Jerry, who will briefly be showing us the coding and training of the model.
After training the model on lots and lots of data, we can now evaluate the model's prediction. The graph here shows the position, x of t, of the mass attached to the spring for a time interval of 10 seconds. Note that the spring oscillates without losing any energy to the surroundings. Although the model's prediction isn't 100% accurate, it can still predict the output within a reasonably small error. This demonstrates an alternative way of solving problems without having to rely on complex mathematical solutions, and provides a benchmark for further applications. This is extremely useful because not all physical equations are possible to solve. If you are interested, we have a couple examples of these equations in our paper. For these scenarios, scientists would have to rely on numerical methods. The deep learning model provides a much more versatile alternative. For example, once trained, deep models can be applied to the situations with different conditions and requirements, since the model effectively learns the behavior of these systems and generalizes them. On the other hand, numerical solvers would require repeated computations for each new scenario, which is very time inefficient.
Our method of using deep neural networks to predict the data has been a great help in predicting our answers to complex physics problems. As AI systems keep getting better, there will soon come a time where we will be able to predict solutions to problems we might not currently have answers to. This can help us not only apply physics, but might also help us discover some new physics. This is similar to when mathematicians got access to a calculator, as it simplified the manual labor needed to solve problems and helped focus on the harder problems that had a greater impact on society.
Throughout this project, we have learned a lot about the complex mechanisms of deep models and neural operators, giving us insight into how they work. The seemingly magical deep learning model is actually just lots of computations and self-adjustments. We have also learned about complex physical systems that require computers to analyze and solve, providing a pathway for future applications of the deep learning model. We hope that you have found our project interesting and continue to explore the fascinating subject of machine learning and other self-learning models. Before we sign off, we would like to put forward a question. Do you think deep learning will ever be able to replace human intelligence?